That's a ratio of 10. 10 to the power 4 is what, 10,000?
Mm-hmm.
That means this area is 10,000 times that area. Wow, wow. So how do we show that? Well, that means this needs to be so thin, right? Like this. The peak is 10 times bigger than that peak, right? Because of Wien's law. But the area is 10,000 times smaller than this area. You see the difference? Now if we go to a star that's 30,000 Kelvin, what's going to happen? There are stars actually that hot, 30,000 Kelvin. They're going to go down by another 10. And they're going to radiate mostly what? Right, 30,000 Kelvin, they're going to radiate 100 nanometer. Right? 100 nanometer. Which is in what range? From 400 to 700 nanometers is the visible range. 100 nanometers ultraviolet. That star is super hot, super dangerous, mostly giving out ultraviolet. But how about the area under the graph? Okay. Now we increased it 10 times more, right, to 30,000 Kelvin. They're 100 times hotter than us, those stars, right? So now when you go 100 to the power 4, what is that? 10 to the power 4.
I feel like 10 to the power of 8 now.
Yeah, 10 to the power 8, wow.
Cool.
100 million times. So the area of this is 100 million times that, and the area of this is 10,000 times that. Right? This is 10,000 times that. The area of this is 10,000 times that. So if I were to plot this on the graph to scale, I got to show that. Then this one's on like that, and then this one's okay. Then if you go down 10 degrees from us to 30 Kelvin, right? Then those are going to be boom, like almost like a straight line, you know. And the 30 Kelvin, they're going to radiate mainly 100,000 nanometer, right? They're going to radiate 30 Kelvin, 100,000 nanometer. And what is that range? Maybe the microwave? Maybe a radio range. And now what if you go 10 times less than that? 3 Kelvin. Is there something that's 3 Kelvin?
No radiation, right?
Well, no, I'm not at 0 Kelvin yet. 3
almost,
Kelvin.
just a little bit, right?
Little bit. Is there something that's 3 Kelvin? The universe, the microwave background radiation, discovered by the Kobe satellite, right? Discovered by the Wilkinson's microwave and isotropy probe, the WMAP. You guys don't know about that? You guys got to be following up that stuff.
I have a question.
Right? You guys are engineers. WMAP, Wilkinson's microwave anisotropy probe, and the Kobe satellite. They mapped out the cosmic microwave background radiation that's still the leftover of the Big Bang, right? This is the 3 Kelvin temperature. 3 kelvins. This is the universe's temperature. The average temperature of the universe, 3 Kelvin. But certain parts of the 3 Kelvin microwave background radiation are hotter than the other ones. So there's anisotropy. That means they're not perfectly identical. So these ones are the ones that gave seeds to, they became the seedlings to the galaxies. Because the universe was not completely uniform. There was a little anisotropy. Okay? Beautiful stuff, yeah.
Oh yeah, I don't know like how I is related to lambda. Intensity of radiation related to lambda, like how we come up with the graph.
Yeah, there's 2 different laws. One is focusing on the spectrum of the radiation that you radiate, because you're radiating a little bit, you're radiating us humans, we're radiating mostly infrared. And then it goes down quickly. We don't radiate in the visible. Okay, so the graph comes down quicker. So this equation is focusing on the spectrum of radiation and where does it peak.
So wiens.
Whereas this equation is just giving you total radiation that you do irrespective of the wavelength.
That's right.
The total radiation.
So
In other words, this is the integral of this.
Okay.
Yeah, it's like
So
you're getting,
radiation is the integral of the graph. You know.
yeah,
The I lambda graph.
yeah, the I lambda graph. This is called the I lambda graph. This equation was discovered before this, right? But this one it took until modern physics for Max Planck to discover.
So how is wiens law defined? Why is it like 3 million over the temperature?
I think the constant's different.
Yeah, the
I think
constant.
it's-
How,
It's in nanometers. I'm giving it to you in units of nanometers.
oh, in nanometers.
Yeah, you could do it in units of meters or nanometers.
So
I'm
it's
giving it
always-
to you. I'm giving it to you in nanometers, so because most of the radiation we know that is visible is in nanometer range.
So is it always 3 million nanometers?
Yeah, over T.
Okay.
So ultimately, the universe is also a radiator. Okay, and it's radiating in what range? What range does it peak in? Microwave, which is an example of a radio wave. Right? So the microwave that you have to cook food is a small little sample of the universe. The universe is just a big microwave. Right? It's the same range of the microwave that you cook food. So that means literally if you put food in the outer space, should you be able to cook it?
No.
Well, I guess it should, because it's radiating in the microwave region.
Oh, yeah.
But the problem is maybe it's coming from everywhere.
The pressure.
Huh?
The air is too.
I mean, ideally, if you're basically inside of a big microwave, and if you take food in and put it in outer space, it should warm. But probably it's not going to work. Okay, so microwave and isotropy probe. Okay. So the other one was the Kobe satellite. But the WMAP was a newer version of the Kobe. Cosmic Background Explorer. So that's why they compare the two. Cosmic Microwave Background Kobe is the radiant heat left over from the Big Bang. The Wilkinson Microwave and Isotropy Probe was launched in June and has made a map of the temperature fluctuations of the CMB radiation with a much higher resolution, sensitivity, and accuracy than the Kobe. You see. So because we were trying to focus on the microwave background, the Kobe mapped it out, but we wanted to know the differences of the microwave background. Some portions of it are 3 Kelvin, maybe other portions of it are 3.00002 Kelvin, and then 2.99995 Kelvin. So those differences are what gave seedlings to galaxies. Okay, the parts that were not the same. Okay, going back to this, so now let's focus on how much you radiate versus how much you absorb. By the way, this is also how, when you go to the doctor's office now, and they want to know your temperature, they put a little gun, a heat gun in your ear, right? Because if you're running a fever slightly, your temperature is gonna go up, you're gonna radiate more. So that gun is measuring how much radiation that you are emitting. And from there, transferring that to a digital number of what your temperature reading is, you see. So when you're slightly warmer, your temperature reading is going to be higher. So P total is going to be P radiated minus P absorbed. P radiated is A E sigma T of the object to the power 4 minus A E sigma T of the surrounding to the power 4. Right? So you're constantly radiating to the atmosphere, depending on what your temperature is to the power 4. And you're also absorbing from your surrounding, depending on what the temperature of the surrounding is. So generally speaking, are we warmer than our surrounding? We talked about that before, right? Yeah, so we are radiating usually more than we're absorbing from our surrounding, which means that we should be cooling down, but we don't because of the biology of our bodies, right? So I'm going to call it AE sigma TO to the power 4 minus TS to the power 4. That their symbols are a little bit different. TH to the power 4 minus TC to the power 4. Okay? Okay, now that we have that established, it's nice to do like a little problem. I'll do similar one that I did in one of my demos.
That easy, but Grammarly can help. This sentence is grammatically correct, but is wordy and hard to read. It undermines the writer's message, and the word choice is bland.
Come to an example on radiation. We have here a glass beaker. The glass beaker is at an initial temperature of 80 Celsius. The mass of the glass beaker is 400 grams. Let's see, which one did I do? That one is a pretty good one. And then the other one,
you have to understand one thing about directing, that every project you get involved in, ultimately, is just going to find its way to breaking your heart. They say there are only 7 stories. I think there might only be 1 story.
Okay, this one.
You have to understand one thing about directing, that
Okay, welcome back. Now I'm going to do a problem with I'm calling radiation of 2 spheres. I'm going to have 2 spheres. One is a gray color sphere like this, and one is a black color. Right now I'm warming up the black sphere. So let's measure the diameter of the sphere. So you can see here, I am warming up water, I'm boiling it, and then I have the sphere sitting on it. So let's measure the diameter of this sphere. Then I have a device here that measures the temperature, okay? It's called infrared thermometer. And the way that it measures temperature is that you point at it, it's a laser pointer, and you point at anything, and it measures the radiation coming from that object, the infrared radiation, and based on that you can know the initial temperature of the metal. So right now if I point, at the metal, you see the red spot? So the laser helps you to see what object you're pointing at. And right now I'm pointing at the sphere, and it's showing me 59. It kind of is jumpy a bit. So if I go closer to it here, right now it's showing that the sphere is 95 to 96 Celsius. So if I kind of point at different points along the sphere, the top of the sphere is a little bit cooler. The sides of the sphere, 96, 97. See, we can kind of rotate the sphere. Okay. And now the top is going to be 94, 95. Okay, so let's assume the average temperature of the sphere is about 95. Okay. Okay. So then I can take this sphere out and start my stopwatch, and I can ask, how long will it take that sphere to reach 50 Celsius or some other temperature, whatever temperature we want to choose. So right now it's just starting about at 95 Celsius. So I'm going to take this sphere out. Okay, start my stopwatch. Okay. So now I'm going to put the other gray sphere on there. I'm going to measure the diameter of the gray sphere also. And so let me get the gray one warmed up. The initial temperature of the black was... So for now, for me, let's just do the same diameter, 7.4. I already measured their masses, and their masses were, the black one was heavier, and it makes sense because it's also a bit bigger, right? They're the same material, they're made of lead, so we can now use the specific heat of lead, specific heat of lead. The question is, due to the radiation of heat that's going to be coming out of this bowl, how long will it take it to cool down to, let's say, 50 Celsius? And then we'll test our calculation. So power radiated is going to be sigma A e to the 4 minus T of the surrounding to the 4, right? Surrounding to the 4. That's equal to minus the mass of the lead ball, minus mass of the ball, times the specific heat of the ball, times dT over dt, right? So then the sigma is going to be a certain constant, 5.6696 times 10 to the minus 8. Okay, so for me, let's just do it this way for now. Let's assume they are the same mass and same size. So I'll write the mass of the black ball, 1.58. And the specific heat of lead, it was given to us in joules per gram, 12.8 joules per gram Celsius, right? Is that 12.8? Can't tell if it's point.
Oh, it's 1. Oh.
What should it be? Should it be 12.8 or 128?
1.
The specific heat.
Probably 1.
I have no idea.
Joules per gram Celsius.
Specific heat of lead. Joules per gram per Celsius. Oh, 0.128. Why did I write?
Yes, per Celsius.
Oh, I probably wrote down joules per kilogram per Celsius, right? Because I don't have a point. Oh, okay, yeah. It's 0.128 joules per gram per Celsius. So then if you go to kilogram, it's going to be 128 joules per kilogram per Celsius, right? 128 joules per kilogram Celsius. So I want to know how long it takes them to reach their final temperature, right? Or which one is going to reach its final temperature quicker. So the emissivity of the black ball is going to be 1. What's the emissivity of the gray one? Let's forward it. The initial temperature of the black of lead, the 4, minus T of the, it's going to be a certain constant, 5.8 kilogram. Give us the surrounding temperature is about 26 Celsius, right? Just kind of touch something that's at room temperature, so it's about 26 Celsius. So that it's kind of cool how I use that gun, right? You can just point it at anything. So T of the surrounding is going to be 26 Celsius. One time, these AC guys were in my house fixing the AC. When I saw this gun, I said, I gotta get one of those. So they were looking at, they just pointed the gun at the place where the AC comes from, right? So in our rooms, it would be, where does it come from? Oh, those vents, right, in the ceiling. So you can just point at it, and it's supposed to be a certain temperature, right? If your AC is working good. So then the reading, they said, oh, you see, your AC, you need a new AC. Then I said, oh, dang, how much does it cost? For you, only $8,000 today. Okay, just put it. That little thing did the trick. So let's see here. Where's the emissivity? I never wrote down the emissivity. Well, let's write down. Let's Google it. Emissivity of gray. Emissivity of gray. Body. Oh, that's a great color. I guess I can look at paints from there, determine paint oil gray, 0.94 or something. Okay, so something like that.
Oh, 50.
Okay, so then how do we solve that? So the power total is going to be EA sigma T of the object to the fourth minus T of the surrounding to the fourth. That's going to equal what? That's going to determine the rate of heat loss of the object, right? This is because this is power. So it's dQ, dH, dt. The rate of heat loss. And the rate of heat loss is equal to the what? The mass of the object times the specific heat of the object times the changing temperature of the object, right? dH is equal to negative mc dt, and then over dt. So this is mc dt. So this is coming from the equation for specific heat from chapter 19. No, actually, no, it was at the same chapter, this chapter, right? 20. So negative mc delta t. Now, why did I put negative? Because the dt is going to end up being negative because you're going to lose temperature, right? The object is going to cool down. So since the dt is negative, you need to put a negative for the heat loss, right? Because temperature of the object is greater than the temperature of the surrounding. So for the black object, we have 1 for the emissivity. The area is going to be what? 4 pi times the radius squared, right? So what's the radius? Half the diameter, right? 3.7 centimeters. So 0.037 squared. And then we have here sigma, which is going to be what? Oh, that one is a universal constant, right? What was the sigma? Oh, we wrote it down earlier. What was that? 5.67.
03.
03.
It was 10 to the negative 8.
10 to the negative 8. What's the temperature of the object? The temperature of the object is, we'll just put it as TO right now, because even though it starts at 95, it's not going to stay at 95. So it's going to cool down, right? So it's going to be TO to the power 4th minus, what's the temperature of the surrounding? 26. Is that going to stay 26? Since the surrounding is a bigger reservoir, you radiating to it doesn't affect it that much.
Oh,
You
just
see?
a little.
So it's just
Just a bit. So therefore, we assume that this one stays the same, 26 Celsius. So, but we converted to Kelvin. So 26 converted to Kelvin, you're going to add 273.15 to 99.15. 299.15 to the power 4. Minus the mass of the ball, which is going to be your 1.58. Specific heat is going to be what? Joules per gram, so 128. Joules per kilogram. See, the reason I put kilogram here is because I wanted to cancel with the mass of the ball, which is kilogram. See, so kilogram, kilogram cancel. You see, here. Then you have dt over dt. So then, how do I integrate that? This dt, this is time. This one goes up to the top. This one goes down to the bottom. You see? So now we have here 4 pi squared, 0.037 to the square, times 5.6703 times 10 to the minus 8. dt is equal to negative 1.58, 128. dt over t to the 0 to the 4th minus 299.15 to the 4th. Then we integrate that from 0 to t, and integrate this from the initial temperature to the final temperature. Right? So the initial temperature of the bowl, that's where you put that here. Initial temperature of the bowl. So then you convert this to 273.15. Convert that to Kelvin, you get what? 368.15. 368.15 to the desired temperature. What do you want the final temperature to be? So the question was, how long will it take for this bowl to cool down to 50 Celsius? Right? So then that's my T final, but then convert that to Kelvin. So add 273 again. 323.15. So you got to do this integral, multiply it by this number, and then divide it by that number. That'll give you how many seconds it will take. So this is kind of like almost an exponential function, because the cooler the body is, the less it radiates to the atmosphere. You see? The absorption is the same. It's absorbing the same amount. But initially it radiates a lot, so initially the temperature cools down quicker. But then once you get close to your atmospheric temperature, you don't radiate as much heat. So the time starts slowing down, you see. So it's probably going to take you, let's see how many seconds for this to happen. So this one you're going to do it on the TI, integrate this function. So let's do that. Practice doing this on your TI with the integral function. So you're going to do integral 1 divided by, so x to the power 4 minus 299 you're going to do 1 over x to the power 4 minus 299 to the power of 0.15 to the power 4. Then you're going to do from 368 all the way to 323. And then this number I'm getting negative 8 times 10 to the minus 9. The integral. Negative 8.005 times 10 to the minus 9. Well, of course, that negative will cancel this negative, right? Then multiply it by 1.58. Multiply it by 128.
Oh, that's one.
Right? Then what? Divide it by all of this.